Yeah. Okay, I hope the PPT is visible. So last class we were discussing about optical flow trackers, and the tracker that we were discussing about was the Horn and Shank optical flow tracker, and we discussed that for Horn and Shank or the HS, if you abbreviate that, it is the HS optical flow tracker. Apart from the brightness consistency, it has also put another constraint because it was a problem with two unknowns to be found, basically u and we had only one equation to find that. So what Horn and Shank did was they have introduced another constraint, which is basically the smoothness constraint, and then formulated this as an optimization problem, and this was the equation which they formulated. The first term stood for the brightness consistency, and the second one for the basically the smoothness constraint. So what the smoothness constraint said was, if you take a particular optical flow diagram, the smoothness constraint assumes that if you take a small neighborhood, then the optical flow vectors within that neighborhood will remain the same. And the whole problem would be to minimize the this particular expression over the values of u and v, and basically ux square, uv square, uy square, etc. Stands for the gradient along the x direction and y direction for the various optical flow vectors. That is basically the optical flow vectors are u and v. So this is where we stopped last time, and yeah, so this is an explanation of the same. So what we need to remember here is that there are two assumptions here for this optimization problem. One is the brightness constancy, and the second one is the additional constraint for the second term. That is basically the smoothness constraint, and only if both the assumptions, which is the constancy as well as the smoothness constraint, if only these two are valid, then we can go ahead, or we'll get an optimal solution for the optimization problem. Okay, so now what we'll do is we'll see how exactly we approach this particular minimization problem. We'll see from this equation how we can find out the minimum. Okay, so in order to find the minimum, what we do is we use a method similar to finding the variational calculus. So what that means is, what we do is we differentiate this particular equation with respect to u and then equate it to 0, and again we differentiate this equation with respect to v and equate it to 0. So when we do that, we'll get these two expressions, okay, where here the same definition of each of the variables holds, where fx is a partial derivative along the x direction, then you have fy is a partial derivative of y of f along the y direction, ft is the partial derivative along the temporal axis, and here lambda is basically a weighing factor which says how much is the smoothness constraint within a particular neighborhood that we are considering, and it ranges between 0 and 1. It's just a weighing factor. Then you have del square u. Now this del square u and del square v terms are basically the double derivatives, or it is equivalent to taking the Laplacian operator of the u vector in the first equation and v vector in the second equation. So when you're taking the Laplace derivative, okay, you can also express it as uxx plus uyy. So what we are doing is we are basically taking the sum of the partial derivative along the x-axis and the partial derivative along the y-axis in order to calculate this Laplacian vector here. Okay. So now, given these two equations, what we need to do is basically you're trying to find out what is u and v, right? So in order to find that u and v, we need to know the quantities fx, fy, ft, and del square u for the first term, and for the second term we need to know del square v2. Okay. So in order to find that, what we do is, in order to compute these values of fx, fy, ft, we make use of various masks over here. Okay. So if you observe, okay, what we do is see, when we are calculating the optical flow for a given image, if you remember, we have now optical flow means what? It is basically calculating the gradients. It will have a particular magnitude which shows how much is the motion between two consecutive frames, and you also have a direction which shows in which direction it is moving, right? So that means it needs two consecutive frames in order to capture this particular motion, right, or the displacement of the pixels. So that means if you're when I'm trying to calculate fx, I need to consider two different frames in order to calculate that. Okay, so let me call it the first frame and as a first image, and the second frame as the second image here, right? So for calculating fx, what we do is we use the mask -1 1 -1 1 in order to calculate what is the the derivative along the x direction for the first image, and then again we use the same mask on the second image, and then what is the result that you get, the gradient result that you get from the first image and the second image, we add them together, and that gives me fx. Similarly, to find fy, we use the mask -1 -1 1 1. Okay, so this mask is applied on the first image to get a gradient. Again, this is applied on the second image to get a gradient, and then we add them up together to get fy. Okay, so for fx and fy, these are the masks which are used. Now, to calculate ft, if you see ft is basically along the temporal axis, that is along the time axis. Okay, so when it is along the time axis, what that means is, okay, so you have an image frame here, you have another image frame here. So what we are trying to do is, when you're calculating ft, you're trying to see what is the what are the changes here, okay, along the time axis. So let's say I'm considering a particular pixel point over here, okay, and another pixel point over here. I'm trying to find out what is the difference between these two, okay, between two consecutive frames. So what I do in order to calculate ft is, for the first image I use the mask -1 -1 -1 -1, and for the second image I use the mask 1 1 1 1. So what I'm doing is, I am just taking the pixel information over here, okay, that is in the frame, let's say t plus dt. Okay, if I'm taking t plus dt, okay, so if I'm taking t plus dt over here, for this particular pixel, okay, I take the corresponding pixel here and just subtract it pixel wise. Okay, so that is the same as shown over here. I apply -1 as the elements in the first image. The mask which is used in the second image is 1 1 1 1, and then adding up them up together, I get ft. Okay, so by making use of these masks, we can calculate the values for fx and ft and fy. And what you have to remember is that these are applied for both the frames, because basically what you're doing is trying to find the displacement of the pixel along two consecutive frames. Now, once you know the values of fx, fy, ft, okay, what is remaining is to find the value of del square u and del square v. So once we know that, and lambda is a factor that we fix depending upon how much is the smoothness constraint that we require. So once all these values are obtained, then you can easily solve for u and v, right? Now, how do you find out this particular value, that is for del square u and del square v? We'll see that. Okay, so as I said earlier, del square u and del square v, it's basically Laplacian. It is equivalent to finding the Laplacian, and we've already seen the Laplacian operator earlier, right? So Laplacian operator is nothing but, you can say it is the sum of taking the double derivative, double partial derivative along the x direction plus the double partial derivative which you are taking along the y direction. Okay, or if I'm trying to formulate this double derivative in terms of finite difference, because it's basically pixels that you have, right? You have it in the form of pixel locations. Then I can write del square f by dou x squared in terms of f of x plus 1 y minus 2 f x y plus f x minus 1 y. Now these two equations, we have already seen these in the one of the first few lectures which we have taken. You've already seen these formulas. You can go back and refer to that. So once you have these formulas, when you combine them together to form del square f, this is what I get. Okay, now from this equation, okay, so you have all these neighboring points. So if you are taking, if f of x, y is the center pixel, then these are basically the neighboring points, the immediate neighboring points that you have. Okay, that is top, bottom, right, and left. And then this is the center pixel, and it is, it gives you a value of minus 4. So that means this equation, now I can formulate this in the form of a mask. I can implement this by using a mask and just convolving with the original image. So the mask will look somewhat like this. You have in the center pixel, you have minus 4, because you have fxy, ffxy, the coefficient is minus 4 here. And for all the remaining neighboring pixels that you have it as 1. So 1. So implementing this equation is equivalent to using this mask in order to convolve, or using this mask to convolve with the original image. Okay, so again, this is something which we have already seen earlier, and this is basically the Laplacian operator. Okay, the mask or the Laplacian mask which is used to find the Laplacian of a particular image. Now, this same mask that you see, if you're just trying to normalize that, or trying to make the center pixel equal to 1 here, I can write it in this form, where all these values becomes minus 1 by 4, and then this center pixel, it becomes 1 here. Okay, so that means equivalently we can make use of this mask also in order to find out the Laplacian of the particular image. So we are finding this, or we are using this in order to find out the values of del square u and del square v. Okay, so as we said, we were discussing about these two equations, right? So for these two equations, we saw how we can find out fx, fy, ft, and we also saw how we can find out del square u. Okay, that is by making use of this particular formula. Okay. Now, what we see is that using this particular mask, okay, on the image is equivalent to writing it as the original image minus the average. Okay, that means if you think of the Laplacian operator, it is basically trying to find the gradient, right? It's a double derivative that you're finding, so that would be the edge information which is present in the image, right? So if you're trying to visualize this, if I'm taking the original image, and then if I take an average image, so average image means basically it's a blurred out image, okay, or you have smoothened it to the finest level, so it's a blurred out image. So if I try to subtract the blurred out image from the original image, what I get would be the edge information. Okay, so you can think of finding the Laplacian of the particular image or patch by just taking the average or smoothing that particular patch and subtracting it from the original patch or original image. Okay, so that is also another way of finding it. So that means I can replace this del square u as writing it as u minus uav, that is using this particular equation of finding the Laplacian, right? So what I do is, if I replace this, I can rewrite the equations as shown over here. Okay, everything else remains the same. Only thing that I do is, instead of writing it as finding the Laplacian of u, I write it as u minus uav, where u is the center value, okay, this particular center value that you have, and uav is basically the average value of the four neighborhood, that is taking all these four immediate neighborhoods, which you are avoiding, or you are discarding the diagonal neighborhood pixels. You are just taking the immediate adjacent neighborhood pixels, okay, that is in the top, bottom, left, and right. Okay, so if you consider those neighborhood pixels and take the average and subtract that from the center value, okay, you can replace that in terms of finding the, or instead of finding the Laplacian operator. So you get these two equations which is shown over here. Now what you can do is we can try to then just solve those equation using an iterative method. Okay, so what we do is, if you have two images in the sense, if you have two consecutive frames, what you do is we can compute two arrays u and v. So basically this u and v are for the optical flow vectors, and if you remember, when you're trying to calculate the optical flow vector for a given image, or so optical flow vectors means you might have different gradients along with directions. You may have regions of no optical flow, that is no movement. Okay, you might have regions with a movement and so on, right? So these optical vectors, when you're calculating optical flow vectors, u along the x and v along the y directions, right? So these arrays will have the same size as that of the input image frames that you're using. So how we formulate this in an iterative way is, first we will compute these two arrays u and v. Okay, and we are basically trying to find an initial estimate. So initially we are going to estimate u and v as all zeros, in the sense that we are assuming that there is no motion over there. Okay, then we use the equations we just discussed right now. We use that equations to find the values of u and v. So so in order to use the equations, you need to first find out, or you need to first compute fx, fy, ft, uav and vav using the masks which were discussed earlier. And once we know these quantities, what we do is we substitute that in the previous equations, and then the only values that need to be determined are u and v, right? So accordingly we update the values of u and v. Okay, so as shown in these equations over here. Okay, now once we have the values for u and v, what we can do is we just try to repeat the process once again. Okay, so that means with the new estimated values of u and v, I can try to repeat these process once again. Okay, in order to update the values of u and v. So once you iteratively try to find the estimate for u and v, there would be a point where the values for u and v does not change much. Okay, so that means at that point we can say that we have reached the convergence. So once we reach the convergence, or once the u and v converges to a value, then we can stop with the iterative process. Okay, so this is how we the Horn and Schunck optical flow tracker or tracking algorithm works. So what we do is, as I said earlier, we find the partial derivatives along the x direction, the y direction, and the temporal axis, and we also find out the Laplacian operator or the edge information, and we make use of these two equations in order to find out the values or the optical flow vectors u and v. And as I said earlier, how we got these equations were, we put the assumptions, or we took the assumptions of brightness constancy as well as the smoothness constraint. That is, the optical flow vectors are smooth, okay, within a particular small neighborhood. Okay, so as an example, let us consider these two synthetic images. So this is the original synthetic image that you have, and the one on the right hand side is a translated version. So let's say this the inner square box over here has been translated by 1 pixel, just 1 pixel alone. Okay, so if you compare these two images, if we just look at it, it doesn't seem like there has been a motion. Okay, because it's just 1 pixel apart. But let us see, when we are trying to track the particular object, let's see how the optical flow tracking detector would give the result as. Okay, so here what we see is that now, using the previous assumption or the previous iterative process. Okay, what we see is in the first iteration, okay, it might just give a value like this. So what we're considering is for the previous image, okay, we know that we do have a small square in the middle, and what we saw is that the motion between the two consecutive frames, in this case the motion here is that this particular square has moved to the right side by 1 pixel, right? So we are trying to see how the optical flow vector or the optical flow tracker will try to identify this. Okay, so when you are going through, or when you're trying to implement the Horn and Shank optical flow algorithm, okay, in an iterative way, after one iteration you see that the result that you get may not be accurate. Okay, so if you see here, not all pixels are updated with the correct value of the optical flow vectors, but after a few iterations you see that, see, after 10 iterations we can exactly capture the information. So this all shows that there is a movement along this direction. Okay, and if we observe, we see that the length of all these optical vectors are also the same, which means that it has moved along this direction, okay, by this particular amount. So this amount or the length indicates 1 pixel in this case. Okay, so this would be how. And if you look at all the remaining outside background regions, you see that there is no optical flow vectors, in the sense there is no significant gradient values or direction which is obvious, right? So that means that the background remains uniform, there is no motion in the background, whereas there has been a motion within the square region over here. Okay, so this is how the output of the H's optical flow tracker would look like for the given synthetic example. Okay, now what we were discussing till now is the Horn and Shank optical flow tracker. Okay, so there are now, that is one very simple method by which we can track the optical flow. Okay, that is basically the pixel displacement between two consecutive frames. Now there are various other methods also by which we can calculate the optical flow. And another method, a better method, is the Lucas and Canad optical flow tracker. Now, in this method, we'll just discuss how it approaches this problem and what is the solution for that. Okay. So if you recall, when you're taking the optical flow equation, you have one equation and two unknowns, right? So this is the equation that you have, that is fxu plus fyv is equal to minus ft, okay? And the two unknowns that you have is u and v. So when you're trying to find the optical flow diagram, what you're trying to do is you want to find the values of u and v, but this is the only equation that you have, right? So in the case of Horn and Shank optical flow tracking algorithm, what they did was they had assumed an additional constraint and then formulated that as an optimization problem. Okay, and we have already seen how iteratively it will try to converge to a solution, right? Now, in the case of Lucas and Canad tracking algorithm, what they do is, again, it starts with the same initial equation. So you have one equation and two unknowns, and here they make we do have the brightness constancy as well as the smoothness assumption, but there is a slight variation in the smoothness assumption. Okay, that is, in this case they assume that the optical flow, okay, they have the same values of u and v within the small neighborhood that you are considering, but the gradients are different for each and every pixel. Okay, so like for example, if you're taking a 3 by 3 neighborhood, let's say, okay, so every pixel in the 3 by 3 neighborhood will give you one equation. Okay, therefore we will have 9 equations, because what it is assuming is that u and v values, they remain the same. okay, but the values of the gradients that you obtain for each and every pixel is different. That is being assumed. So if that is different, then what happens is these values, you do not have, the fx is not uniform throughout. You'll have different values of fx and fy for each of the pixel that is being considered. So 3 by 3 neighborhood means you do have a center pixel over here, okay, and then when you're considering the 3 by 3 neighborhood, you have 1 2 3 4 5 6 and 7 8 9, right? So therefore you get 9 different equations, and for each pixel you are assuming different values of the gradient, right? Now what they do is that now what you have is 9 equations. That means you have a system of linear equations, okay, and then just like how you solve a system of linear equations, they proceed further with these 9 equations which are present, okay. So what they do here is, as I said earlier, at each and every pixel, okay, the values of fx, fy, ft, it will be different. So because these are different, you will have a set of 9 equations, okay, for every pixel that you are considering. So that means what you have now is you have 9 equations and just 2 unknowns, right? And therefore it would be easy to solve this problem. All that you do is you can just all these 9 equations, system of linear equations, I can simply write it in terms of a matrix form, okay. So if I write it in terms of a matrix form, I can write it as fx1 fy1 fx2 fy2 etc to the fx9 fy9, because you have 9 equations, and then into uv is equal to minus ft1 till ft minus ft9, okay. So or this one I can also write it in the matrix form, which is given like this. You have matrix A into matrix U is equal to ft, and as you know, you have the known quantities, these fx1 fy1, basically the gradient information which is present. These are information that can be computed, and even ft1, these are quantities that can be computed, and the unknowns that you have is just u and v. And by solving this system of linear equations, or this matrix form, you can easily find out what is the value of u and v, okay, and that is basically our optical flow vector. But here one thing is, if you're trying to find out, so here you have to find out what is the value of this matrix u, right? So if you're trying to find out the value of matrix u, what happens is, what you need to do is, I need to take a to this side, so I'll have to write it in terms of u is equal to a inverse ft. So how I write this would be, I'll get it as u is equal to a inverse ft, okay. So if I can just calculate a inverse and then multiply that by ft, I can find out the value of u. But the problem over here is that when I'm trying when I'm trying to calculate a inverse, here if I observe, now this is the matrix A, right? And this matrix A, it is having a dimension of 9 cross 2. Okay, that means what you're having here is not a square matrix. So because it's not a square matrix, here finding the inverse is difficult, right? So because you cannot find the inverse of A in this case, and so it's not, you cannot directly calculate it as U is equal to A inverse FT. Okay, although this equation holds, we cannot calculate this way because you cannot find the inverse in this case. So what we do instead is, we try to, instead of taking the inverse this way, you try to make use of a pseudo inverse. Okay, as shown in this particular slide here. So what we do is, instead of taking AU is equal to FT, because you cannot find the inverse of this matrix A, and in order to make this a square matrix, what you can do is, I can rewrite the equation in this particular form. I can write it as A transpose AU is equal to A transpose FT. I'm just basically multiplying both LHS and RHS by A transpose, and I get it in this form. Now when I take A transpose A, what happens is, now this becomes a square matrix, right? Now when this becomes a square matrix, it is possible for me to find the inverse of A transpose A. So therefore now my solution becomes U is equal to A transpose A inverse into A transpose FT. Okay, so therefore this A transpose A inverse is my pseudo inverse, so pseudo inverse that I'm using, and now I can just solve this equation by just using this expression, which is U is equal to A transpose A the whole inverse A transpose FT. Okay, and then that would give me the solution of U. So this is how we can make use of the Lucas and Canade optical flow tracking algorithm. Using, now here it is written least square, it is not using least square. The approach that you're using is just the solution using linear algebra or the system of linear equations, that's all. So when you're now least square is another method by which you can implement the Lucas and Canade and you can find the solution, which we'll be seeing later. So far what we have discussed is that in the Lucas and Canade optical flow tracker, we assume that for each and every pixel you have different gradients, and therefore you get 9. For if you are considering a 3 cross 3 neighborhood, you get 9 different equations. We write it in matrix form and try to solve that to find U and V. And since the matrix that you are using is not a square matrix, you can make use of this pseudo inverse in order to find the values of the matrix U. So here this matrix U has both U as well as V as elements, and that is basically the optical flow. Okay, so this is one way by which you can approach the Lucas and Canade, that is by solving using system of linear equations. And now another method is using least square, which we'll see in the next slide. Okay, so another method by which we can approach the same problem or the same equation of the Lucas and Canade is using the least square minimization approach. Okay, so here as we were discussing earlier, what we are trying to do is we are trying to estimate U and V. Okay, and what we have here now is we have 9 equations, right? And for the previous case, we considered it as a system of linear equations. Now here what we do is all these 9 equations, we try to formulate this in the form of a least square minimization problem. Okay, so what we do is in order to find the value of U and V, this particular equation which is shown here, okay, this summation equation, we try to minimize this. Okay, and that is the least square fit problem, right? So if you look at this, what we have is sigma I fxi u plus fyi v plus ft the whole square. Okay, so you are just taking the square of these gradients over here and summing it over I, okay, which is over the neighborhood that we are considering, right? And then you are trying to minimize this problem. So in order to minimize this, what we can do is we can just differentiate the function with respect to u and then equate it to 0, and again differentiate the function with respect to v and equate it to 0, right? So what we would get would be like this. So what you're doing is you're just differentiating both the equations with respect to u and v, and then you're writing you're equating it to 0, and just after expanding the opening the brackets and rewriting, you'll get these two equations. Okay, and these two equations you can write it in matrix form as shown over here. Okay, so finally now what we have is I can write it as sigma fxi square, sigma fxi fyi, here sigma fxi fyi, sigma fyi square. So this matrix, if you see, it is basically a matrix which is containing gradients. Okay, it is just gradients. So you have the square of the gradient along the x direction, you have the product of the gradients along the x direction and the y direction, and the summation shows that you're just summing it over the neighborhood, right? And what you're trying to get here is basically the gradient information along different directions. Okay, and if you observe this equation right now, what we see is Now this matrix which we are using is a square matrix. Okay, that means we do not have any problems with finding the inverse, and we can directly find out the values of u and v. So by formulating it as a least square minimization problem, we are able to get it in this equation where you have a square matrix over here and where we can easily find out the inverse. So after finding the inverse, it would be like this. Okay, you're just taking it to the other side. You'll get this as a final equation, that is uv is equal to all the gradient information inverse, okay, into minus sigma fxi fti and minus sigma fyi fti. Okay, so since all these gradient information or all these gradient values are known to us, okay, the only unknowns you have is u and v, and just by solving this matrix form, you can easily find out the values for u and v. So this is the Lucas and Canad problem, or the optical tracking algorithm with a least square minimization approach. Okay, now what we see here is an example of using the Lucas Canad optimization algorithm, which we have just seen right now. Okay, so here if you let me see if I'm able to find that out. Yeah, so here for this okay, for this particular video sequence, okay, we are trying to find out, or what we are doing is we'll take different frames of this video sequence which you just show which was just shown to you right now, and we'll try to see how the optical flow, the Lucas and Canard optical flow algorithm would look like. So I'll just play this once again. So what you observe in this video sequence is that, okay, you have the tree moving over here, okay, and it is basically the movement of the tree that we'll see how that is being captured. We'll have a look at that. Okay. Okay, so on applying the Lucas and Canard least square optimization algorithm, tracking algorithm on the video sequence, which was just shown to you right now, this is the result that is obtained. Okay. So in this result, if you observe all that you see over here, all these points that you see over here, or all these marks that you see here is basically the optical flow vectors. And all these optical flow vectors, it gives you a particular direction in which each of the pixel moves between two consecutive frames, and it also the length gives you the information on what is, or how much it actually moved. Okay, it is depending on the motion, the speed, okay, by which it is moving, or how far it has moved. Okay, now one thing which you observe here is if you just take the bark area. Okay, 1 minute. Now, if you just take this bark, tree bark area, okay, and try to zoom that in, you see that this is how the optical flow vector looks like when you're trying to implement the Lucas and Canard optimization, which we just discussed earlier, okay. And what you observe is that you see within the bark region, you see optical flow vectors which shows different values, as well as different, slightly different directions also. Okay, basically different values for within the tree bark region. But one thing which you know is with the video sequence which you just saw right now, basically the movement of the whole bark is the same. If you're considering each and every pixels within the tree bark, the movement is the same, or the displacement of each of the pixels between consecutive frames would be the same. So what that means is right now when you have these information or these patches of optical flow where it shows that there is not much displacement, then that means there is something wrong. Okay, this result that we got is not exactly correct. Okay, because what we are expecting is the optical flow vectors to have the same magnitude as well as almost or let's say significant gradients, okay, which is almost uniform within the tree bark region, because all the pixels are expected to move uniformly there, right? Now, what could be a reason that this is happening? So again, if you remember in the video sequence which was played, one thing you can observe is that since the tree is very near to the video camera which was used to take the video, what happens is while the vehicle is moving, you can see that the tree bark region is actually moving fast. Okay, so that means when you are see in the Lucas and Kennard algorithm, what we are assuming is a 3 by 3 neighborhood, and we are trying to what we are trying to determine the displacement of the pixels by considering just a 3 by 3 neighborhood. Okay, but what happened is that in the video sequence, the displacement information of the tree bark, it was too fast, in the sense the displacement between the two frames is more than the 3 by 3 pixel neighborhood which we have considered in the case of Lucas Canal. So because it goes out of the frame, or it is not within this 3 by 3 neighborhood, it is not able to capture that motion, and that is why you have these large variance or large difference in the optical flow information which is obtained within the whole tree bark, which actually has the same kind of displacement. Okay, so what that means is that this particular optical flow algorithm, that is a Lucas Canard optical flow algorithm, it will fail in areas of large motion. So if you have certain regions or objects which have got a large motion or a large displacement with respect to two consecutive frames, then it fails. And the reason for which it fails is because you have this constraint of a 3 by 3 neighborhood, and the displacement is too fast to be captured within the 3 by 3 neighborhood. So what we do is, as a solution for this, okay, in order to ensure that even for large motion such displacement can be captured, we can make use of pyramids. Okay, so pyramids in the sense the Gaussian pyramids. So if you remember, in Gaussian pyramids, what is assumed is, let's say you have a particular image. Let's say this is the original image you have. Okay, so when you're finding a Gaussian pyramid, what you're trying to do is you're basically just subsampling the original image, right? So when you're subsampling, you get a smaller image this way, right? Subsample it further, you get another image here, okay? And each of these reduces by a factor of 2, right? And like that, this goes on. So you might have the smallest element over here, right? So the same image, the same original image that you are considering, you can kind of create a Gaussian pyramid over here where you just subsample the original image, okay? And so you have one subsampled image here, another subsampled image, and so on, and until the the lowest level you can keep subsampling it, and it would be in the form of a pyramid, and that's why you call it as a Gaussian pyramid over here, right? So what we can use is this Lucas Canard algorithm when you're trying to implement. Instead of simply implementing on the original image only, you can also you can form a Gaussian pyramid and then implement it on subsampled image. So when you're implementing on the subsampled image, what happens is, or how it is advantageous is that now each of the subsample image has different scales, okay, of the same object, right? So let's say you have a particular object which is having a fast movement or a large motion, in the sense it is a fast movement and it is not able to be captured within 3 pixels, right? So let's say as an example, in the original image, let's say if the displacement of the tree bark, okay, is within 16 pixels. That means only if you're considering 16 pixels can you capture the motion. Let's say, let us assume that if it is 16 here, what happens is when you're trying to subsample this original image in the next level, what you get would be maybe the same displacement information can be captured within just 8 pixel region, okay, or when you're again subsampling it, it could be captured within a 4 pixel region, and here within a 2 pixel region, and so on, right? So what happens is, now if you are implementing a Lucas Canade or optical flow tracker, and since it is considering a 3 pixel region, at this particular subsampled image, what happens is it would be able to accurately capture what exactly is the displacement between pixels in the frame. And the reason being, here, since it is the motion can be captured within a 2 pixel region, and we are considering a 3 pixel region over here, that means that displacement can be captured. Whereas in the other cases, especially the original case, since it is too fast, it won't be able to capture the exact information, okay. So this kind of approach can also be used in Lucas Canade, okay. That means you can consider the original image as a Gaussian pyramid and then apply the Lucas Canade on different subsampled images in order to overcome the limitation of not being able to capture large motion or fast moving objects. So here this is an example of the Lucas Canade optical flow tracker, which has been implemented along with using the Gaussian pyramids. Okay, so since you have considered different subsampled images and the displacement has been, you're able to capture the displacement properly. So if you're just trying to zoom the exact region, you'll get it in this form. Okay, and now if you observe, you see that within the tree bark region, the optical flow vectors you see is more or less having the same magnitude as well as direction, right? So we see how uniform the optical flow looks like right now. Okay, so this is the improvement of the Lucas Canade when you're trying to implement it using the Gaussian pyramids. Okay, so as a conclusion over here, we were discussing about the Horn and Schunck optical flow method as well as the Lucas Canade optical flow method. And for both of these methods, one limitation is that if you're just taking the original method or algorithm as such, it would work only for small motion. So small motion in the sense, if you have slowly moving objects over here, okay. So in order to overcome that, what can be used is we can make use of Gaussian pyramids in order to ensure that we will be able to compute the large optical flow vectors as well. Okay, now coming to some limitations of using the flow-based trackers. So some limitations is, now the first type of broad type of tracker that we saw is the detection based tracker, right? So in the detection based tracker, you need to build an object detector, okay, for that particular object, and we need to apply it on all the frames, right? And let's say if you have some kind of changes in the illumination, probably the detector that you're using may not be able to detect the object properly. So that is one limitation of the detection based tracker. Now when you come to flow based trackers, what we see is there could be a tendency to drift. Okay, so what that means is, let's say if there is some kind of error in the determination of the displacement. So what we are doing is we are considering two frames, right, and we are just trying to find out what is the displacement of each. Let's say you have two corresponding pixels and you're trying to find out what is the displacement of these two pixels in the two consecutive frames, right? So let's say if there is an error in the determination of this displacement between the two frames, what happens is that would reflect in the consecutive frames also. So each time if there is an error, that kind of accumulates within each of the other frames, and therefore when you're trying to calculate the trajectory, there might be a tendency to drift apart. Okay, so that is one disadvantage of using or of having the flow-based trackers, where if there is an error, that may get accumulated over the consecutive frames. Now, there is also another limitation of the flow-based tracker, and that is basically with respect to the object appearance. Okay, that is, let's say if the object appearance changes between frames. Okay, so right now for this particular frame, if I'm considering this leg region alone, this is how the leg region looks. Okay, and for the next frame, let's say, so this person is basically walking, right? So this leg has moved to the front, and this is how the image looks like. And if I just take the leg region alone, this is how it looks. Okay, so if you observe these arrow points over here, right, you see that if I consider, see, this particular region here and this particular region here, the appearance kind of changes, right? And if you're considering this region as well as this region also, the appearance in the sense, the illumination as well as the variation in which the pixel intensity varies within that particular region also changes. Okay, in these two cases, like for example at these points which are shown, right? So in such cases, what happens is when there is a difference in the object appearance between different frames, like for example, if the colors are different or the illumination changes abruptly, or the variation in the texture is different, what happens is there would be a difficulty or a limitation of the flow-based trackers to identify the tracking properly. Okay, so this is another disadvantage. Okay, so far what we have discussed was about the optical flow tracking algorithms, right? We had discussed about the HS as well as the LK, that is the Lucas Canad optical flow trackers. Now, apart from these, there are also other advanced methods which can be used to capture the motion of objects. Okay, and one such method that will be studying next is the KLT tracking algorithm. Okay, it's basically for Canada Lucas Tomasi tracking algorithm. These are named after the scientists who have developed the particular algorithm. So before moving on to the KLT tracking algorithm, the very first step in the KLT tracking algorithm is to find corners using the Harris detector. Okay, so what we'll do is we'll first discuss about the how the corners of a particular image can be determined using the Harris corner detector, and then after having discussed that, we will move on to the details of the KLT tracking algorithm. Okay, so first let us see how we can find the corners. Okay, just give me a minute. Okay, yeah, so continuing with how to find the corners, right? So corners means, now let's say you have an image over here and you have some objects here, right? So for those objects, you might have some corners. So let's say I'm having an object that looks like this. Let's say you have corners over here. You have 1, 2, 3, 4, 5 corners. Now, how do you find out corners given a particular image, right? So we'll just see a very simple approach by which you can, find that, right? So how we find the locations of the corners is, uh, given a particular image, we can first find out or calculate the gradient, and we can simply try to scan the image in order to find if there is a sudden change in the gradient. Like for example, let's say this is the image that I have, and let's say this is one corner which I'm having. Okay, let me just leave out the other details of the object, right? And let me just consider this particular corner, and I'm trying to calculate or find out or determine this corner over here. So first what I can do is I can calculate the gradient. So when I calculate the gradient of the image, let's say I'm getting these edges. I get this edge here and I get this edge here, right? So by calculating the gradient, we get the edge information. Now what we can do is, given the edges, is there a corner present, right? So one very simple approach by which you can do that is, you can simply look at whatever is the gradient information or the location of the gradients. We can just scan through the and through the given lines or the edges and see if there is any abrupt change in the direction, right? Like for example, let's say you have this particular direction, right, this particular edge information here, right? So as I'm scanning through this, okay, what I see is that, okay, there is a sudden change in the direction of the edge and it has gone down. So when there is an abrupt change or a sudden change in the gradient direction, I can say it indicates the presence of a corner. Okay, so that would be a very simple explanation, or very simple method by which we can say that there is a corner. But the problem here is that we cannot, finding corners is not as simple as that. Okay, we cannot simply just assume the method that we just shown here. The reason is, when you're trying to find the gradient of a particular image, in order to ensure that the noise has been suppressed within the particular image, we usually smoothen the image and then find out the gradient, right? So when we smoothen out the region, what happens is that there is a tendency for all the the corner regions to get blurred out, right? So basically smoothing means you're just trying to blur it out. So what happens is, instead of getting a sharp edge, okay, sometimes what we may get is, because of the smoothing operation that you have, okay, you might get a kind of a curved edge over here, right, instead of a sharp edge. So when you have this curved edge, right now there is no sudden change in the gradient direction over here. Rather, there is a gradual change, okay, from one direction to the other. It keeps changing and changing, and then you have it here, right? So the problem here is that, because of the smoothing that happens before finding the gradient, okay, here the corner details also may get kind of smoothened out, okay. So because of which the gradient information itself that we get, okay, may not be the correct estimates or very sharp estimates. You might get it as a little poor estimates of the gradient, right? So what we can do in such a case is, we can go across with a slightly different approach of finding the corners, okay. And for that, what we assume is, we make use of two important effects of the corners, okay. One effect is the large gradient. So what that means is, let us say we are considering a small neighborhood around the corner. So let's say you have this neighborhood and you're considering a small neighborhood around this corner over here, okay. And what we assume here is that, if there is a corner, or if I'm considering a region with a corner over here, then it will have gradient information, non-zero gradient information over here, which are large in values also, okay. As in, so if you're trying to calculate the gradient along this direction, you do have a gradient, right? Here also, when you're trying to calculate, you do have a gradient. And because there is a corner present over here, the gradient magnitude that you have is large. And if you look at the direction, which is the second one, right, the orientation should swing sharply. In the sense, there would be a large difference in the orientation, right? So the two properties of the corners is that, one, if you consider a small neighborhood region which is having a particular corner and then calculating the gradient, okay, we see that the gradient values will have large non-zero values. And another property that we assume, or that we will notice, is that it will have two or more directions, or it would have directions which are swinging sharply, okay. That means there is a large difference in the directions of the of the gradient also. Okay, so making use of these two important properties of the corners, we can try to see how the Harris corner detector would help to detect the corners. So let us say you have an image where this is the object. Okay, that is, you have this edge here and this edge here. Okay, that is the object, and this is the corner which is present. Okay, now in order to understand how the corner detection problem works, let us try to consider, or let us try to assume three different scenarios. This is the first scenario you have, this is the second scenario, and this is the third scenario. So in the first scenario, what we are assuming is, let us say we are considering a small patch or a small window which is a flat region in the sense there are no edges present. Okay, there are no corners present. All that you have is a uniform background region. Okay, or more or less uniform homogeneous region is present within the window that we are considering. Okay, that is the case one, or the scenario one. In the second scenario, what we are assuming is, let's say you're considering windows which is having an edge. It has an edge, but there are no corners. Okay, and the third scenario which you're considering is the corner, that is a window which contains the corner. So you have a corner over here. If you are assuming this image, you do have a corner over here and two edges which goes this way as well as this way. Sorry, this is supposed to be a straight line. This goes this way like this, and straight down like this. Okay, and this is the corner that you have. So let us assume three different scenarios, or three different window regions: the flat region, the edge region, and corner region. And let's see how the information regarding the corner is different from that of the flat region and the edge region. Now if you're just visually looking at this, what we see is, now here in this flat region, okay, the flat region does not have any kind of edges or corners. Okay, and it's just a uniform homogeneous region over here. So what we see is there is basically no gradient information which is present, right? So in this case you do not have any gradient information, and regarding the direction also you have no change in directions, basically because you do not have a gradient information. Now there may be some gradient information if there is some noise present, but as far as this particular image is concerned, you have no gradient information over here, right? So that is a flat region. In the second scenario, where you have a window with an edge region, what you see is, now you have an edge here, right? So because of this edge, you will see that there would be a gradient value, okay, which is a non-zero gradient value would be present, but there is no change in direction between these windows that you're considering here, right? So here there is a gradient, but there is no change along the edge direction. Okay, so that means here there is no particular corner which is present. And if you are considering a corner image, what we will observe is that you do have gradient information, or the gradient vectors are present. Okay, and these gradient vectors are large non-zero values which are present, and also there are significant change in the direction of the gradient vectors which are present here. Okay, so these are the three different scenarios, right? And let us see how we can interpret this mathematically, and how we can make use of these three concepts in order to detect which region has got a corner. Okay, so this is an example which just shows how the gradient looks different for the three different regions. So let's say you are considering an image where you have a linear edge. So this is the linear edge that you have. The second scenario where it's a flat region, flat in the sense you have a uniform region. Uniform in the sense it's a homogeneous region. There is more or less, the pattern or the texture which remains over here is the same. Okay, you do not have any specific edges over here. And a corner region where you see that, okay, you have a particular square here and another here, and basically the corner which would be present would be somewhere here, right? Except if you're not considering the boundaries, you have it over here. Okay, Now, if I'm trying to calculate what is the partial derivative along the x-axis, okay, so let me just denote this as ix, okay, which is basically the partial derivative of the image along the x-axis, and let's say I'm taking this particular patch here as iy is a partial derivative along the y-axis, okay, and let me assume that I'm just trying to plot the gradient of the given images along the x direction and y direction. So in the case of linear edge, what I see is here in the linear edge you have an edge like this, right? So if I'm taking the x directive or in the ix, I see that there is a gradient information which is present at the same location as shown in the original image. You can observe that there is the edge information over here, or the gradient shows that difference, right? But if I'm taking iy, what I say is that there is no gradient information which is present. So what that means is I do not have any linear edges which are kind of horizontal here. I just have a vertical linear edge in this case, okay, and that is given over here. Now, if I consider a flat region, okay, what I see is there is just some noise which is present. So you see that when you're taking the partial derivative along the x direction and y direction, I do see some kind of some kind of values over here. Basically, the because of the noise which is present over here, you do have some information, but it is not a significant gradient vector. Okay, all these values, these are just because of the noise. You do not have large non-zero values here, or basically you do not have any significant gradient vectors both along x direction and y direction in a flat region. And if I'm considering a corner region, when you have a corner region, what you see is that along the x direction you have a significant gradient vector, along the y direction also you have a significant gradient vector. Okay, so this is a visualization of how the gradient vectors would look like if you are considering the three different regions, that is with an edge, flat region, as well as with a corner region. Now the same thing we can also plot that in terms of a graph, that is I can plot Ix versus Iy and see how the distribution of the gradient vectors would look like. Okay, if you're considering the same previous example. Okay, so what we see is, so if I'm considering a flat region, right, a flat region where you have just a little noise throughout, okay, but the basic underlying image or region is the same. So in that case, when I'm trying to find the gradient along the x direction and y direction, I do see that there are a few gradient vectors, but it is not significant. Not significant in the sense, it is, if you're looking at the magnitude, okay, it is having a low magnitude, and it is concentrated around the origin. Okay, you see that it is somehow just concentrated around the origin, and without much of you do not have any large non-zero values for the gradients over here. Okay, so by looking at this distribution, you can kind of assume that it is almost a flat region that you see, because you do not have any significant gradients over here. But if I'm, let's say, if I'm taking a linear edge region, okay, that is the one which was shown over here. Okay, we have already seen how the visualization looks like if I'm trying to calculate Ix. The same thing if I'm just trying to plot that Ix versus Iy, what I see is here along the Ix, I see gradient vectors which are having large magnitudes, but along the y direction, I do not see much of variations or much of large significant gradient vectors. So there is significant gradient vectors along the x direction, but not along the y direction. Okay, so what I can say is that in the linear edge, you have the more gradient vectors, significant gradient vectors along the x direction or the Ix. Basically, Ix would be a significant factor here. And if I'm, let's say, taking an image with a corner, right, what I see is I do have significant gradient vectors along both the x direction as well as the iy direction. Or I can say that I have large non-zero gradient vectors along both the directions. Okay, so if you look at these three scenarios, you see that the whole distribution of the vector points in the sense the gradient points that you see along the x direction and y direction, that itself is different. Okay, so all three regions have got a different appearance of the distribution of the gradient points, right? So what we do is we can make use of this information, this difference in the distribution pattern, in order to find out or in order to try to estimate which region has got the corner, okay, has got the presence of a corner. So for that, what we do is we can try to fit an ellipse, okay, in the given data distribution. So when we are trying to fit an ellipse, let's say in the flat region, it could be an ellipse or it could be a circle, okay, which is fitted over here. But what we see is that the axis, that is the major and minor axis, which the values of that would be less, because all that you have is a very small ellipse around the origin, right? So the values of the ellipse axis would be small. But if you're taking a linear edge, what we say is, if I'm trying to fit an ellipse, it might look somewhat like this. And you'll see that the major axis would have a much larger value as compared to the minor axis over here, right? So by looking at this ellipse, we can say that, okay, so this is a region which has got a particular linear edge along this particular direction. Okay, so by looking at the ellipse or comparing it with this, we can make out that difference. Again, if I'm considering, let's say, a corner image, in the corner image, when I'm trying to fit an ellipse, what I get would be, now since it has got large non-zero values along ix as well as iy, you need a much larger ellipse to fit in these, right? So what that means is, here right now the values of the major and the minor axis for this ellipse is going to be large, right? Both the major and minor axis is going to have a large value. So by looking at this graphical representation itself, we can try to understand how different the distribution is for all three regions, and we can easily say that, okay, so the ellipse which has got the larger specific values of the gradient vectors along x and y direction, okay, when you're trying to fit an ellipse and find the axis, if it has got a large value for the axis, then you can say that that particular region has got a corner. So what we do is, when you're trying to mathematically try to implement that concept, okay, instead of saying we fit the ellipse and try to find out what is the value of the major and minor axis, what we do is we basically try to formulate that as a matrix and try to find the eigenvalues of the matrix. So what we do is we define a particular matrix which is given as H is equal to sigma along the particular window that we are considering, delta I transpose. Okay, I can expand this to get this particular matrix. Now here, if you see this term over here, okay, this is nothing but the partial derivative along x direction, so this is nothing but ix. Okay, this is also ix. Well, what I see here now, this term here is basically iy, okay, and the rest of the things are same. So here what I'm doing is I'm trying to calculate ix into ix. Okay, here what I have is I have ix into iy. This is ix into iy. Here also I have ix into iy, and here what I'm having is iy into iy. Okay, so if you look at this matrix, it is nothing but again trying to find out the gradient, the partial derivative along each of the directions, and I'm just trying to group it in terms of the horizontal, that is the ix square, ix iy, and iy square together, right? And this is the matrix that I have. right? And here this G sigma indicates that we are trying to smoothen, so it's for the Gaussian blur. You're trying to smoothen the image first using a Gaussian blur and then trying to find the partial derivative. Okay, so once you have this matrix, what you can do is you can just find out or compute the eigenvalues, and by looking at the values of these how small or big the values of the eigenvalues of the matrix are, you can say what kind of a region it is. Okay, so just like in the previous case, we just saw that if you have a small ellipse where the major and minor axis is having a very small value, correspondingly the eigenvalues of this matrix would also be small. Okay, then you can say that whatever is the region or the window that we are considering is basically a flat window or a flat region. Flat in the sense it has got constant gray level, or more or less, if there may be some noise but which may get smoothed out with this, right? So you have a homogeneous region or a constant gray level region is what it says. Okay, now, let's say if you're having a window with an edge region, then what happens is when you're calculating the eigenvalues, one of the eigenvalues will have a large value. Okay, so that means along that you'll have a linear edge, one edge along that direction. And let's say you are having a window with a corner. In that case, both the eigenvalues will have large values. So by simply calculating or defining or computing this particular matrix, okay, which is basically a matrix of the gradient information, and then trying to find out the eigenvalues and just looking at what are the values present in the eigenvalues, I can easily say whether the given region or the window that we are considering is a corner region or not. Okay, so this type of corner detection method is called as the Harris corner detector. Okay, and here you can see an example of how the Harris corner detector looks like. Okay, I'll just take 5 more minutes for this, and then we will have the quiz. Okay. Okay, so when you look at the response or the Harris corner detector for this image, what we see is that it is able to detect the corners at some of the points. Okay, for example, this particular point here and okay, this particular point here and some of these points here. Okay, it is able to detect the corners. Okay, but there are some corners, like for example the corner over here or the corner over here. These are some regions which are not detected very clearly or properly in the image. Okay, so that is one disadvantage of the Harris corner detector. That is, if you observe these two regions, you see that here the tip of this pencil and the background has almost the same intensity, or there is not much intensity difference between this corner as well as the background. So if in case the corners lie at regions with a background having the similar intensity, pixel value intensity, what happens is it won't be able to calculate the gradient properly. And since the Harris corner detector is dependent on the gradient, you see that the corners may not be detected properly. Okay, but if let's say you do have a large difference between the corners, okay, the corner intensity as well as the background, you see that it would be able to detect that properly. Okay, so here what you see is this is the output response of the Harris corner detector, and this image is just overlaying that on the original image to show how exactly it is able to detect the edge points or the corner points here. Okay, so Harris corner detector, it is a simple method by which you can find the corners using the concept that we just discussed earlier. But the problem is that it would work well only if the intensity of the background as well as the object is large enough, okay, for the gradients to be more prominent. So because it is heavily dependent on the gradient, unless and until you have a proper gradient information, it wouldn't be able to properly detect the corners. So that is one disadvantage. But one advantage here is that it is unaffected by translation and rotation. So what that means is, let's say you're trying to, take an image and you're trying to rotate it. Like for example, you have this image, okay, and you have the corner which is detected here, and you're trying to rotate this image, let's say, okay. So even if the initial image is rotated, but still it would be able to find out where the corner is, okay. So even if you're trying to rotate an image or translate a particular image or an image patch, what happens is the Harris corner detector is not affected by that, okay, because even if it is rotated or translated, what we are considering is a small window region, and within that window region how it varies, right? So it is invariant to translation and rotation, so that is one advantage. Okay, so we'll stop here and I'll just launch the quiz now. By the time, if you have any doubts, you can ask that now.
Excuse me, Professor.
Yes.
Is there any standard reference material we should be referring to for just, you know,
For the computer vision as a whole, or specifically for object tracking?
for computer vision as a whole, actually?
Okay, you can refer the textbooks which were initially discussed in the first class. In the first class, you were given a reference. There were two or three textbooks, mainly the first two references.